Okay, today I want to talk a little bit about the what's called the Cauchy-Schwarz inequality, which is the subject of the fifth lecture post. All right, and this is an inequality that is about Euclidean spaces. So what does that mean? Just to recall what that means, a Euclidean space is something that looks like a vector space V, which is also equipped with a scalar product. Okay, so that means that this scalar product is a generalization of the familiar dot product in Rn. All right, so this is something that takes two vectors and pairs them together and gives you a real number back, subject to certain axioms. It has certain properties. So in particular, the scalar product of V with itself is always a non-negative number, and in fact, the scalar product of V with itself is equal to zero if and only if V is equal to the zero vector. And then what else? So V is also, the scalar product is also bilinear, right? So if I write down something like alpha 1 V1 plus alpha 2 V2, beta 1 W1 plus beta 2 W2, you can expand using the FOIL identity from high school algebra, right? So first, outside, inside, last. That's explained in the notes. Okay, and then there's also symmetry, so that the scalar product of V with W is the same thing as the scalar product of W with V. Okay, and if you have a scalar product on your vector space, then you can define a notion of length, which is typically called norm. So the length of a vector V is the square root of its scalar product with itself, okay? And this generalizes the formula from uh, from high school algebra, which is that the length of a vector x is equal to the square root of x dot x, okay? Just in Rn. So it's a generalization of that. And then also you probably know that in Rn, there's a formula that says something like x dot y is equal to the absolute value of x, so the length of x times the length of y times the cosine of the angle between them. And actually, we want to use that formula in the setting of an abstract Euclidean space to actually define the notion of angle. So cosine theta, where theta is the angle between two vectors, is the ratio we get if we actually had the general version of this, right? So we would write down cosine theta. We want this to be the definition of the angle between V and W, right? Which would mean that cosine theta was the ratio of V dot W, or V scalar product W, over the norm of V, norm of W, okay? Let's say this is the angle between two non-zero vectors, okay? So the denominator here is not equal to zero. And in order for this to be true, well, we'd need to somehow know that this is actually a solvable equation, right? And for theta, a number that's between 0 and 2 pi. So an angle anywhere between 0 radians and 2 pi radians. And in order for that to be the case, we need this ratio to be between -1 and 1, right? Because the cosine of any angle is between -1 and 1. And that's where the Cauchy-Schwarz inequality comes in. It tells us that that actually is true, and it's something that can be deduced entirely from the axioms for a scalar product in an arbitrary vector space. Okay, so it can be written like this. So Cauchy-Schwarz says that for any two vectors, for any v, w in V, we have what? So here's one way to write it. The scalar product of V with W times the scalar product of V with W. So if I mix together V and W and taking scalar products, and I do that twice, that's less than or equal to what I would get by taking the product of these pure scalar products, which don't mix v and w, right? So scalar product of v with v and scalar product of w with w. Okay, and moreover, it says that this is not only true, but it says that with equality, if and only if v, the set consisting of v and w, is linearly dependent. Okay, so the first part of the proof, which justifies the fact or proves that this inequality is true, that's done for you in the lecture notes. And the second part is part of the assignment, showing that equality holds if and only if v and w is linearly dependent. So let's go over that because this is one of the problems on the second problem set. And so first observation is that this is definitely true if v or w is the zero vector, right? Because then this set v with w is definitely linearly independent, is linearly independent, and also both sides of the Cauchy-Schwarz inequality are zero just by the fact that scalar product of 0v with anything is the number 0, right? So just like ordinary multiplication, 0 times anything is 0. Okay, so so what about v not equal to 0? So neither of these things, neither of these two vectors are equal to the 0 vector. All right, so let's see what happens there. And this is really about analyzing the proof that's presented in the Lecture 5 course post, blog post. And so how does that proof work? So it says that what one can do to understand this Cauchy-Schwarz inequality is look at the function f of x defined by f of x is equal to inner product of v minus xw, v minus xw. Okay, and so here v and w are two fixed non-zero vectors in your vector space V. Okay, so if I use the FOIL identity to expand this out, I can write this function down in a different form, which gives me some insight into what it actually is. All right, so if I expand this out, I will get f of x is equal to, and you should sort of make sure you know how to do this calculation. Maybe I'll just do it in one step, but I'll say what I'm doing. So first is v with v, right? Outside is minus x v with w, right? That's because you can pull the x out of the scalar product, and the inside is minus x w with v, and then the last is plus x squared w with w. Okay, or in other words, simplifying this a little bit, f of x is equal to scalar product of w times x squared minus 2x times, let me write that in the other order, minus 2 inner product of v with w x, and then finally plus scalar product of v with v. Okay, And another way to write this, which maybe makes it look more familiar, is this is f of x is equal to ax squared plus bx plus c, where we know what these numbers are in terms of v and w. So a is the scalar product of w with w. B is -2 times the scalar product of v with w. And then finally c is equal to the scalar product of v with v. Okay? So what kind of a function is this? It's a quadratic function, in other words, known as a parabola. All right, so in particular, a is bigger than 0. Okay, why is that? Why is that? That's because this is the scalar product of a non-zero vector with itself, so it has to be a positive number. All right, so a is bigger than or equal to 0, which means that that f of x is an upward opening parabola. Okay, and also we know that f of x is bigger than or equal to 0 for all x, because f of x by definition is equal to the inner product of v minus xw with v minus xw, which is bigger than or equal to 0, right? So this is the scalar product of a vector with itself, so it has to be non-negative. So that gives you some idea of what what the graph of this function f of x looks like. So f of x is a parabola that looks like, so there are two possibilities. Let me take this off. Let me draw two coordinate axes. And then, okay. So it either looks like this, all right? So that's a parabola that lies strictly above the horizontal axis, all right, the x-axis, or copy that, paste it. It's a parabola that looks like this, okay? That is tangent to the x-axis at one point. It can't dip below it. Okay, and how do you differentiate between these two cases? Well, what is this this possible tangent point here? This is the solution of f of x equals 0, right? So this is the solution of f of x equals 0. And so is this, and this says that equation doesn't have any solution, right? This says that the equation has exactly one solution. Let's call it x0, right? And this says that there is no solution to the equation f of x equals 0. And how do you differentiate between those two cases, right? So if you have a quadratic equation, ax squared plus bx plus c is equal to 0, then what does the quadratic formula tell you? It says, I hope I remember this, x is equal to minus b plus or minus square root b squared minus 4ac, all divided by 2a, right? That's the quadratic formula, hopefully. And this piece of the quadratic formula is called the discriminant. So d is equal to b squared minus 4ac is called the discriminant of a quadratic equation. And why is it called that? Well, because it tells you what's happening, right? So this is this formula here says that I can rewrite this as square root of this number capital D. All right, let me write that capital D. And you know what happens with square root? If D is a positive number, then there are two square roots of that number, right? Plus or minus square root D. And if D is 0, it has a unique square root, which is equal to 0. And if D is negative, then nothing, all right? So we actually want to see what's happening here, right? So so this discriminant for us, so if D is, let's see. So let's write this down. So this case here is discriminant less than 0, right? No solutions to your quadratic equation. And this case here is discriminant equals 0, exactly one solution to your quadratic equation. And what's the discriminant for us? So let's remember, so D is equal to what? For our particular quadratic equation, f of x equals 0. So let's go back and copy down this data that we have. All right. Put it here. Okay. B squared minus 4AC is equal to, so B squared is 4 the W, and that's B squared. Okay, and minus 4AC is minus 4 V with V and W with W. So if D is strictly less than 0, right, then what does that give me? That gives me scalar product of V with W, V with W is strictly less, whoops, not very good writing, strictly less than scalar product of V with V times W with W. Okay, and if D is equal to 0, then that gives me actually equality between these two quantities, right? So V with W, V with W, actually equal to V with V and W with W. So what are we actually trying to prove? So this first case, the discriminant negative, meaning this parabola does not actually touch the horizontal axis, is what's handled in the lecture notes. And we want to analyze the case where the discriminant is actually equal to 0 in a little bit more detail. Okay, so the case where discriminant is equal to 0, and we want to show that this can actually only happen if V and W are linearly dependent. So, so let's see what happens, right? So, no. So we want to show that discriminant is equal to 0 if and only if VW is a linearly independent set. Linearly dependent set, sorry. Okay, so so that's two things to show. So suppose first that VW linearly dependent. Okay, what does that mean? Since V and W are non-zero vectors, this means that that X is equal, no, not X, that V is equal to X times W for some X not equal to 0 actually, but that doesn't really matter, for some real number X. Okay, so V is a scalar multiple of W, or conversely, W is a scalar multiple of V because this X is not 0. And that means, the function, let me call it the parabola. So the parabola f of x equals v minus xw, v minus xw. Let me call this x0, okay? x0. F of x, so the parabola f of x v minus xw, v minus xw satisfies, did I spell that right? Yeah. Satisfies f of x0 is equal to v minus x0w, v minus x0w. All right, and v minus x0w is the zero vector, right? V is equal to x0w. So this would be 0, 0 is equal to the number 0. Okay, so that says that actually if v and w are linearly dependent, then the discriminant of this quadratic equation actually is equal to 0 because there is a solution to f of x equals 0, right? So that means that we're actually in this d equals 0 case. Okay, so that's one direction. So since this means that f of x equals 0 has a solution, the parabola f of x touches the x-axis, and we get equality in the Cauchy-Schwarz inequality. Okay, so that's one direction, right? So that shows that if v and w are linearly dependent vectors, then we are in the d equals 0, discriminant equals 0 case of how this quadratic equation is behaving, which means that we actually have equality in the Cauchy-Schwarz inequality, right? So I remind you, we did this little calculation here where, all right, this is saying that d equals 0 implies we have equality in the Cauchy-Schwarz inequality. Okay, so what about the other direction, right? Suppose that what? Suppose that f of x 0 is equal to 0 for some x0 in R, okay? I.e. that the discriminant in this quadratic equation is equal to 0. This means that f of x0, which is by definition equal to the scalar product of v minus x0w with v minus x0w, is equal to 0. And now what does that tell us? Well, so this is, one of the axioms for the scalar product. This is the scalar product of a vector with itself, okay? And in order for the scalar product of a vector with itself to be equal to 0, that vector has to be the 0 vector. So this implies that v minus x0 times w is equal to 0, which in turn implies that v is equal to x0 times w, which says that v is a scalar multiple of w, right? So vw is a linearly dependent set. Okay, and in this case, equality does hold in the Cauchy-Schwarz inequality. All right, so we've just shown that equality in Cauchy-Schwarz implies the W linearly dependent. Okay, so if you put those pieces together and write them up maybe in a little more clear and formal way, you will have yourself a solution to the Cauchy-Schwarz problem on problem set 2. All right, and so that's how that works. And and I would urge you to just sort of in a different direction, think of examples of Euclidean spaces and see what the Cauchy-Schwarz inequality says in those specific examples. So the first thing you might think about is Rn, right? So Rn with the dot product, what does the Cauchy-Schwarz inequality say? It effectively says that, let's write it down. Let's write it down like this. So it says that the dot product of a vector v with a vector w times the dot product of that same vector v with w is less than or equal to the dot product of v with v times the dot product of w with w. Okay, and if let's write this out more concretely. So if v is the vector x1 through xn, and w is the vector y1 through yn, what is this saying? This is actually saying that, so what's the dot product of v with w? This is x1, y1 plus all the way up to xn, yn, right? Repeat it twice. So squared is less than or equal to the, what's the dot product of v with v? It's the sum of the squares of the components of v times the sum of the squares of the components of w. So what we've actually done when we've proved the Cauchy-Schwarz inequality is we proved this real number inequality here, which is kind of a non-obvious real number inequality, without actually referencing the dot product at all, right? So this inequality between real numbers actually doesn't have that much to do with Rn or with the dot product, in the sense that the only properties of the dot product you need in order to ensure that this is true are the axioms for the scalar product, for the general scalar product. All right, so this is not nearly as specific as you might think if you just looked at this particular inequality. So what's another example? Let's take another example. So let's say that v is equal to the vector space of let's say continuous functions. Continuous functions f from the unit interval 0, 1 into the real numbers. Okay, that's a perfectly valid vector space. So if I have two vectors in this space, so a function f of x and a function g of x, what is their sum? Well, this is the function f plus g of x, which by definition evaluates, so that if you put an input x into here, f plus g of x outputs the sum of f of x and g of x. Okay, so this is what f plus g means. Okay, and scalar multiplication is defined in the same way. And how can you define a scalar product in this space? Well, this is one that's very often used. So the scalar product of f and g is the integral from 0 to 1. So you integrate the product of f of x and g of x over your interval dx. Okay, and so you can check, and you should check, that this satisfies the scalar product axioms. And since it does, or remember you need to check that, since it does, this means that the Cauchy-Schwarz inequality holds, right? So that means we can say that the scalar product of two functions f and g squared is less than or equal to the scalar product of f with f and g with g. And what does that actually say, right? So this says that if I take the integral from 0 to 1, f of x, g of x, dx, and I square that whole quantity, right? This is less than or equal to the integral from 0 to 1 of f of x squared. Let me write the 2 over here. Um, typically people write f squared of x. All right, it just looks a little cleaner. So f squared of x dx, which really this just means, I just don't want to confuse you. This is just f of x times f of x. All right, times the integral of g squared of x dx, which is definitely a pretty non-obvious statement. So why would this be the case where the product of these two integrals, where you mix f and g together, is bounded by the product of these integrals where you don't mix them, right? So where f goes with f and g goes with g. And that's a kind of a pretty non-obvious statement. It's not really, maybe immediately clear how you would just prove this using calculus per se. But actually, in a sense, it doesn't have anything to do with calculus. It is just an artifact of the Cauchy-Schwarz inequality, which holds in general Euclidean spaces, right? So once you verify that this scalar product here really is a scalar product, all right, in the vector space of functions, continuous functions from 0, 1 to r, then this inequality follows automatically by the general proof that we've given for the Cauchy-Schwarz inequality, which is, I hope, kind of indicative of the power of doing things in this degree of generality. I mean, this just says, whatever Euclidean space we write down, we're going to get a version of the Cauchy-Schwarz inequality holding for that particular Euclidean space, because we know it holds in general. And that particular version could be pretty interesting, like this inequality between integrals, or like this inequality between sums. Okay? And so that is my speech on the Cauchy-Schwarz inequality, and I will leave it to you to explore.